very much. Welcome to my talk. My name is Gabriel Camilleri, and I will be talking about Rubik's Cubes in the fourth dimension. So, I will split my talk in essentially 3 parts. First, I will go into what the fourth dimension is, then I will go into what Rubik's Cubes are and why they're interesting, and then we will combine everything together. So here on the first slide, what we're seeing is the fourth dimensional cube, which is called the tesseract. So for intuition, we will go through the sequence of dimensions, essentially. First, we have R0, which is the infinitesimally small point. So we can do nothing, essentially, with this, unless we repeat this an infinite number of times in a direction. We're going to call it x, which is what we're most familiar with as the real line, right? And now the most familiar ones for us would be the 2D Euclidean space and the 3D Euclidean space, which are always repeating the previous one an infinite number of times in a new direction. So this goes y, this is this, y times this way, and z times this way, repeating the previous one always an infinite number of times. And now, the same thing for r to the 4, we will repeat the 3D Euclidean space in a new direction, w, an infinite number of times. And to explain this further, let's imagine we are, because the main way we understand the 4th dimension is by looking at the comparison between 3 dimensions and 2 dimensions. And then we go a step up and see what the parallels would be. So let's imagine we have a 2-dimensional friend called Pepe. And suppose I want to be very mean to Pepe, and I want to throw a ball at Pepe, okay? Imagine this ball would be a perfect sphere. I'm going to throw it at his world, his 2-dimensional world. What he will see is first an infinitesimal point, and then a circle, or annulus, and then another circle, It goes bigger and bigger until it reaches its maximum size, which for that circle, the diameter will be equal to the diameter of the sphere. And then it will start shrinking again until it becomes another point, and it disappears. And Pepe will go to his friends and no one will believe him what he saw. So this is how we understand it. Now if we extend it to 4 dimensions, or the 4-dimensional hypersphere, which is just a sphere in 4 dimensions, it will, if we imagine it coming towards our 3D Euclidean space, we will see exactly the same thing. But instead of a circle, we will see a sphere. From an infinitesimal point, grow to a maximum size sphere, and then it will start shrinking down. And again, no one will believe us, because what even is that? Okay, so that's enough for the 4th dimension for now. And what are Rubik's Cubes? So they are more generally known as sequential move puzzles, just like these. And normally we are concerned with regular ones, so n by n by n in 3 dimensions, right? So the number of ways this can be configured is 43 quintillion, that large number, not as large as the stated numbers. So essentially, these are only the legal configurations. However, there are way more illegal configurations. For example, if I twist a corner, that's illegal. So if we consider all the configurations and identify all the ways to get to each configuration from the solved state, and then see them as the same thing, right? Doing 4 right turns or up turns is the same thing as doing 4 right turns. They are the same configuration. So let's identify all of those algorithms as one thing. And then let's add this composition operator, which will be all of those configurations. You do one algorithm, and then you do another algorithm. So you do one thing like this, then you do another thing like this. So that's called composition operator. If you add that to the set of all configurations, you form a group, which is this very interesting mathematical structure, which essentially describes symmetries. And in a group, you have these 4 axioms. You have closure, which means doing one legal algorithm after another, you don't get another shape, you still get a cube. And this is a legal configuration because we never did something illegal like twisting a corner. We have associativity, which is this technical term, which basically means if I do X, I move X, and then compose with a move Y, and then after that I do another move Z. It's the same thing as doing X, and then I compose it with the result of doing Y and then Z. Then we have identity, which is an operation which is a configuration or algorithm where we just do nothing. Obviously, we can just look at it. We can also turn it around. This doesn't count as a move, and we're not changing the state. And we can also do, for example, 4 turns of the same face. They're all identity configurations. It's still one thing. It's still one operation, one configuration, but it's different algorithms for the same thing. So the inverse is also very interesting because it tells us we can solve the cube. If we do any algorithm, we can reverse it and get back to the solved state. And then this extra property, which is it's not an axiom, but it's called non-abelian because this group is not commutative. So if I do this and then this, you don't get the same thing as you did the opposite, this and then this, right? In general. Okay. Now, what's God's number? So, God's number is essentially, let's imagine we are gods, and we know we can see every possible state of the Rubik's Cube, and we can say exactly how, and the fastest way to get from one state to another, so the fastest algorithm. We are more interested in the worst possible case of solving this Rubik's Cube as a god, right? So the best case, so minimum, but the worst case, so maximum, because we're optimal, so minimum, and worst case, maximum. So minimax value it's more commonly known. So the way God's number is found is computationally by intelligently searching through the state space of the Rubik's Cube. And it's proven, it took quite a long time, over 15 years, to prove that it's 20 for this Rubik's Cube. Basically by finding a lower bound and an upper bound, and then you just keep using computers to converge on one number. Some common misconceptions. So these positive dimensions, if I say a 3 by 3 by 3, they're not being multiplied by each other. For example, if 3 times 2 times 3, if they're being multiplied, you would assume, let's do times 1, the same thing, right? Times 1, times 1, times 1, they can keep saying times 1, but no, it's not the same thing. Because one of them, the 3 by 3 by 3, is this. I can hold it in my hand. The second one is a 4-dimensional object, and it looks like that, if you project it on a screen. Also, so that's very important, but now, something else very, it's called misconception, is that since we define a Rubik's Cube by how the cubies, the small cubes, are positioned relative to each other, so this and this are the same thing. A 2 by 2 by 1, for example, I can't show it here because it's regular. But if I had a 2 by 2 by 1, which is also called a floppy cube, and turn it around and look at it in another way, you can also say it's a 2 by 1 by 2. So they are commutative in that sense. And for notational simplicity, I won't keep saying 2 by 2 by 2. I will just say 2 cubed, or 2 to the 4 for this one. So what we're looking at here is this cube split in half and projected. So we can see every single face in color. So splitting it down the middle here. Even though it says 2D 2 by 2, it's a bit misleading because the puzzle itself lives in 3 dimensions. So if we had a 2D Rubik's Cube, in reality we wouldn't be able to scramble it, right, or solve it. Either case, you either have all of the colors being the same or all of the colors being different. You would need a 3rd dimension to actually scramble it. So what this is just this projected into 2D. So what we need to do now is define what the moves are, right? So what doing this is, every single reorientation or move, because those are 2 different things. So these are the legal rotations. So for example, a front rotation, which to be exact is a reorientation, so it's just this, is represented like this. So both hemisphere or half cubes are turning simultaneously because both the front and the back are turning, right? So that doesn't count as a move. Now the gyro reorientation, this is another, we're not changing the state again, it's a reorientation. But the gyro has a specific definition. It is when we do a reorientation in a higher dimension than what the puzzle is being represented in. So this is 2D, so a gyro rotation would be something like this. So you're changing, you need the third dimension to do that. If you look at the previous one, this didn't need the third dimension, but here we need the Z here to do this. And this is represented in this way. So it basically looks like you're breaking the puzzle apart, but if you look, in reality it looks, so it's still solved, right? Every face still has the same, the colors are all the same. And now an actual twist, so an actual move. The front twist, which is this. If you really think about it, this is all we need to do all the things, because you do the twist and then you can just reorient it however you want. And this looks like this. So only half of it moves. And now you can see it's not solved, because the middle one has red and yellow. Right? Now, let's go to the fourth dimension. So, the 2x2 by 1 by 1 is the, so a 2x2 by 1, I've already mentioned, is the floppy cube. Looks like that. It's a very boring puzzle, very small state space, you can't do much with it. So we want to see what the four-dimension version of this would look like. So now, instead of 3 axes of rotation, we're going to have 4. We're going to have to rotate it in the 4th dimension. But of course, we need more colors. We can't just have the same amount of colors, because we need more faces. So, how many colors should they have now? Let's reason about this using a sequence of cubes. So, if you think about the cube, a cube, this has 6 faces, so 6 colors. Now, if you go back to 1 dimension, to a square, you can't talk about faces anymore, because you only have 1 face. So you have to talk about edges. 1, 2, 3, 4. So now you have 4 colors. You can color it with 4 colors. If you go again 1 back, you go to a line, which is 2 colors, because now we can't talk about edges because you only have 1. We talk about vertices, so you have 2. 2 colors, 4 colors, 6 colors. Reasonably, what comes next is 8. And that is in fact what we have, 8 colors. Now, this is what it looks like. So this is the 4-dimensional version if you were to project it onto 3D, and then again onto 2D because you're looking at it on a screen. But if you count the colors, 1, 2, 3, 4, 5, 6, 7. So if you really think about it, where is the 8th color, right? The 8th color, we can't see it, because let's explain this using going back 1 dimension, right? So if you look at this, you can see 1 color right now. If I turn it around like this, now you can see 2 colors. I can do better, however. If I show you a corner, you can see 3 colors. We can do even better than that, though. If you look at it in this way, we look at the front face, and we remove the front face. So what you get when you remove the front face is you can see the back face now, like you're opening a box, right? You can see not only the back face though. You see the back face. You can see this face. You can see this face. You can see this face, and even this face. The only thing you can't see is the front one. If you put the front one, you would only see 1 face. So you can see 5. 1's missing, just like here, 1 is missing. So in here it's a face that's missing, and here it's still called a face, but it looks more like a 3-dimensional object, like this. And this is the 3D printed version of a 2x2 by 1 by 1. So why is this the 2x2 by 1 by 1? So how is this constructed? So I didn't break the 3rd dimension. We're still in 3 dimensions, don't worry. We're using magnets, because so far we don't have a way to use the 4th dimension. So we use magnets. These are just 4 QBs, they're called, magnetically stuck together. So naturally the question is, what are the legal moves, right? How can we show that this is the same thing as the previous one? So the legal moves are, so you can do this. So doing that twice comes back to the original version, which is, I call it a transversal because it sounds cool. So a transversal move. Don't worry, it's not very good. So that's there. I have a second one. But that only uses the third dimension. How is that? It's boring, you know? It's kind of like doing the floppy cube. But to use the fourth dimension, we need a gyro move, which is how I described before. A gyro move here would be rotating every single QB like this. So you see, wait. The white face, so the colors are white, yellow, pink, and then the corners, right? But if I do a gyro, if I turn each one of these like this, now white is nowhere to be seen because it's on the inside face. And now purple can be seen, which you couldn't have seen before. It is the same thing as we saw before. Purple was not seen in the image before. Oh, and then there's the half gyro, which would be the twist in the fourth dimension. So it's not actually, it's changing the state now. Like the gyro doesn't change the state, but the half gyro, which is just like doing that on half of it, is actually a twist, is a move. Now, is there any illegal configuration? And yes, there are a few. For example, I can't just quarter gyro, so I can't grab one QB and turn it around. And I can't also grab a QB and move it. I can't grab a QB and twist it like this. Like this. That's also breaking the puzzle. There are a few others, but I won't go into them. But what goes number for this puzzle? Like we talked about, 20 is for this. And fun fact, 11 is for the 2x2. In the fourth dimension, we can still talk about God's number. And for this puzzle, given that it doesn't have a huge state space, it's still quite big, but not as big as the 43 quintillion. The answer can be found computationally in about 30 seconds. If you brute force it, not even doing it intelligently. And I don't have time to go through it, but these are the ways to basically how you'd find it. And now this is the 2 to the 4. Quick note about it. It's the same exact thing. Same amount of colors as the 2 by 2 by 1 by 1. And this is just a video just to show you that it is doing what this is doing, just in 4 dimensions. So I squeezed all the faces together, and it looks exactly like this, with just some different colors. And in fact, it has the same amount of colors. If you ignore the core, which is white, that's the same thing. And in fact, there is a 3-dimensional counterpart for this, which is this. And this is the assembled version of this. So I haven't had the time to assemble it, but it would look like that. Hopefully, eventually, it will be assembled. And in fact, brute forcing God's number for this puzzle in the same way, in the unintelligent way I did it before, it was 10 to 20 years to take. Obviously, there probably is a better way to do it, but fighting coding isn't very good. And that's basically all. Any questions?